In this video, we will be talking about chiral carbons with R and S configurations, and we will show a couple of examples of how we can apply this R and S configuration to sawhorse projections. Now, I want to mention that Fisher projections are actually probably the easiest to show this, and probably one of the most reliable methods to demonstrating R and S configurations on a chiral carbon. But typically on a test, you will be given a sawhorse projection, and for that reason we will try to solve them from a sawhorse projection. So I want to mention that a typical method used to specify the configuration, also known as absolute configuration of a chiral carbon. And we are going to, number one, verify that we are working with 4 different groups attached to a carbon atom. So we need to make sure those groups are all different, and if 2 are the same, then we will be unable to assign R or S to our carbon atom, which will therefore make it achiral, and we won't be working with a chiral carbon. Second, we will assign priority to each of the 4 groups, and by assign, we can use the same rules that we use for EZ nomenclature. So the greater the atomic mass is going to equal the greater priority. So I want to clarify that. Now 3, turn the chiral carbon atom so that the lowest priority group is pointing away from the observer. This is something that we try to do, but we're not always able to do that. And when that's the case, we can just use an inversion rule, and we'll be going over that here shortly. And 4, determine the relative orientation of priorities, counting from 1 to 4. So what does that mean? Well, if we're counting from 1 to 4 and we move in a clockwise direction, we will have an R configuration. And conversely, if we are moving in a counterclockwise direction, we will have an S configuration. So now let's apply these rules and these guidelines to a sample problem. And as I mentioned before, we will show this on a sawhorse projection. So let's start off with something like this, where we have, we'll say 2 hydrogens. On top we will add a methyl group, and we will show a long bond pointing into the background, attaching itself to another carbon. And over here we can just add an alcohol, hydrogen, and methyl. So right away, if we were to try to assign priorities to this carbon, we would immediately see that we have 2 of the same groups attached. So with 2 of the same groups attached, we are not going to be able to assign priorities, and we will not be able to configure an RS configuration. So now let's move down this bond, and we'll go to this carbon. So it looks like we have oxygen, which will have the highest atomic mass relative to this carbon, this methyl group, and this hydrogen. So why did I make this priority number 2 and this priority number 3? Well, whenever we are assigning priorities, we are looking for our first point of difference. And so what I mean by that is this carbon attaches itself to this carbon, and it also attaches itself to this carbon. But if we keep moving out, or if we keep branching out from this carbon, we will now see that we have 3 hydrogens attached to this carbon, and this carbon will have 1 carbon and 2 hydrogens down here. But this 1 carbon will have a higher atomic mass relative to these hydrogens. And keep in mind too that this is not additive. So if it doesn't matter how many atoms we have that proceed beyond this point, we are simply stopping once we get to our first point of difference, and that's when we can assign the priority without continuing. So that is why I assign this as number 2, This is number 3. And hydrogen is going to be the lowest simply because it's going to have the smallest atomic mass. And whenever I'm assigning these from 1 to 4, I'm suggesting that 1 is going to have the highest atomic mass, and 4 is going to have the lowest atomic mass. So that is how we are numbering these in order. So now let's count our priorities and see what orientation we have them in. So if we are counting this as 1, 2, 3, and 4, we are moving in this direction, and we end up with an S configuration. Now, part of the rules suggest that we need our lowest priority group to be pointing away from us. Well, if we are looking at this sawhorse projection, say from this viewpoint, we can assume that this bond goes into the background, and then this hydrogen goes even further into the background. So we know that this hydrogen actually is pointing away from us. So there is no need to invert, and we will just simply keep our S configuration, and that will be our configuration for the molecule. So now let's go on to a different example where we still show a sawhorse projection, but this time we can use wedges and dashes. So let's see here. If we have a molecule that, say for example, we'll show hydrogen with a wedge, and that just means it's pointing toward us. And then we have a dash with an alcohol pointing away from us. And then we have we'll say C6H5. And by the way, C6H5 is simply a benzene ring, and we can verify that by just looking at it like this. So we'll add some hydrogens to this. And we can add this one. And this will just be an R, and that just represents the rest of the molecule. So let's verify that we have 1, 2, 3, 4, 5. So we have H5. And then we have 1, 2, 3, 4, 5, 6. C6. So that checks out. And this R is simply going to be this carbon right here. So I just wanted to show that we are working with a benzene ring and to not be confused by that. So let's continue by drawing the rest of the molecule. So now we have this long bond, as I mentioned before, pointing in the background to another carbon. And we can make another wedge, and we can attach nitrogen and some other atoms to it. So we'll add NH, CH3, and then over here we can show a dash with a hydrogen pointing away from us, and that's going to be convenient when we're counting our priorities. And then down here we can just have a methyl group. So let's start off with this carbon, and let's try to number it in order of priority. So we have oxygen, that's going to be our highest atomic mass. Now it looks like we have two carbons that are competing against each other. We have this C6H5, and then we have this carbon down here. So C6H5, as shown in this diagram of a benzene ring, is simply attached to multiple carbons and hydrogens. But this carbon is immediately attached to a nitrogen. So that nitrogen is going to take priority over all of the carbons in the benzene ring because nitrogen simply has a higher atomic mass. So now we can assign this as number 2, and then 3 will be our benzene ring for our hydrogen. So now we're moving in this direction. We end up with an S configuration, but as you can see, our hydrogen is pointing toward us rather than away. So we just simply invert the configuration and we get an R. So now let's try it on this molecule or this atom and see if we have a chiral carbon here. So nitrogen will be priority number 1. This carbon will be priority number 2. Methyl 3. And hydrogen will be 4. So now we're moving and counting in this direction, where we have an S configuration, and there's no need to invert because our lowest priority group is pointing away from us, and that is what we want. So we end up with an S configuration. So that is how you take sawhorse projections and show S and R configurations to determine their chirality.